Hi, so I'm trying to explain the formal definition of convergence to a limit in analysis 1. And so this is probably the formula you would have seen. I mean, obviously there's different versions of it. I'm using like the funny font L and a comma here, a dot denoting such that, just to make it clear. So as you can see, I just plot the generic sort of sequence, and I added a line to make it more clear because there are some other points which I erased beforehand when I was trying to sketch it before. Anyway, ignore the numbers. It's just for so that you can visualize something. So basically, you can see that the sequence, it converges to a limit, which I've gone and drawn here. So basically what this is saying is it's saying basically for every epsilon you choose, which is greater than 0. So for example here, epsilon 1 at this given point, which I'm going to label n1. Let's say this is n1. So yeah, for every epsilon which is greater than 0, or epsilon being infinitesimally small, there exists a certain threshold number, like n1 in this case, such that every number after that n, so let's say whatever numbers here, in this partition or whatever, they imply that the member of a sequence at that point, the difference between that and the limit is less than epsilon. So just so that you can visualize, basically, so this is epsilon, and you can see the difference. This is the difference between this point or the distance rather, and then the limit is epsilon. So basically, as we keep going forward, we can choose, for example, I don't know, n2 for this case, and n2 will be the right n for which is chosen, exists for a given epsilon, any given epsilon. So for example, I don't know, it's going to be smaller, that's the thing. Yeah, let's just say epsilon 2, and you can keep doing that. So basically the points here after this point, they're going to be all closer to the limit than this given epsilon. So yeah, if you keep going, and you can see that it narrows down to something, because if I draw like a dashed lines, then it would be like yeah, you would just see that it narrows down. So and actually, if I had colored pencils, I would have used that, but I don't. So I'm just gonna, yeah, like you can see that like they're bounded, the points are bounded within a certain region, and as you choose like epsilons which are smaller, then that's going to be like a larger n, and you're going to find that, yeah, I think graphical intuition is an important part of it, because otherwise it's just too many quantifiers, and it's a bit confusing. Yeah, let's say you were to choose a relatively advanced, like let's say, I don't know, let's say this was n6 or something, and then at this point probably you'd look like, the right epsilon would be epsilon 6, and you would see that for this part of the partition, the range, the region where it's bounded is getting very narrow. So it's actually it's approaching the limit itself. So n6, you see, as the x-axis advances, the points are getting narrower and narrower together, closer together to the limit. So again, for every epsilon we choose that's greater than 0, there's going to be some n, such that, like, for all the points after that n, the corresponding member of the sequence, so here let's say this is a 6, like, I don't know, yeah, the corresponding point in the sequence is going to be, like, the distance between that and the limit is going to be less than that epsilon that we have set as a sort of like a boundary thing. Yeah, I hope it makes sense. Like, let's say, yeah, if at some point we get to a stage where, let's say, the points are just like getting very, very sort of like, well, this is not the best drawing maybe, but let's say it gets really, really, really close. It's like, then what? The epsilon is going to be like, I don't know, epsilon 800, let's say, and it's going to be so small I can't even draw it here. And all the points are going to be bounded within this super micro region, and that's basically the definition of a limit in analysis. I hope it makes any sense. Yeah. Yeah.